Count the components, yeah. So today and next week we'll talk about the course projects. Okay, we'll keep working on the same thing for the whole week because I pushed the SD card thing to the week after next. So, but I will still talk about what are the components and connections involved in the SPI. Because you need to know SPI, you need to know I2C. So, but the thing is, we don't have time to work on any of the I2C components. If you want to learn more about it, if you are CE, you will learn it in embedded. But if you are not in CE and you want to pursue that computer digital system concentration, I highly recommend that take the CE351 class with me in the spring. Okay. Look forward to seeing you there. Haley's like, no, don't want to do this again. All right. So including today and so next week, you guys will come over here in the classroom, and I'll let you guys keep working on the course project. I think the final design is due probably Friday next week or some point next week. So I'm giving you guys time to work on it. Right, let's do a good job on the course project. So now the plan for today is first I'm going to show you like what are the necessary connections for which modules on the schematic. If you look at the course website, you can see I just added one more link. Okay, I just added one more link to the major page. It's called the Skyboard design files. So from here you can download it and open up the Skyboard's schematic and layouts in your Ego PCB. So if you cannot find the components for your course project, you can right-click the components in the schematic and find the properties, so you can eventually find it, I think. For most of them, at least. All right? Or maybe just copy and paste. I don't know if that works.
Yeah, that works.
That works? So you can copy and paste from this file. Okay? That's probably will solve your problem. So I'm going to talk about the connections after introducing other sensors and parts available in my lab, so you can think about like what are the modules you want to use. So again, the project itself doesn't have to be super complex. The goal is to have two different modules, and you put in your code you have at least the two SRs and have different states instead of just putting everything in one loop. All right? If you put everything in one loop, that's still the engineering 271 measurement instruments, whatever that class let you guys to do, right? So this is a different class. This is, you guys are considered as experts after this class. I think you will be able to design the independent embedded system by yourself from scratch, right? Including looking at the sensors, the interface, the power supply, and design your schematic, and do the soldering, and put the components on the board, and do the testing. Boom, product. That's the goal, okay? And also including debugging skills. So next time when you are asking me questions about the board, I don't want to hear that, hey, Dr. Lee, my board is not working. All right? That's not a legit question. I don't like it. I mean, before this class, you could ask the question that way, but after this class, I would like to hear that, hey, Dr. Lee, I tested this and this, and I probed this pin, and I saw this on the oscilloscope. And then I think the problem is not this because I tested this and it works, so the problem has to be this, right? And then I don't know what to do after that. That's what I want to hear. Not just like throw everything to me, it's not working. Then I started probing everything by myself and tell you why it's not working. Usually I can figure it out, but I want to let you guys to develop this kind of debugging skills. So I'll give you some examples, okay? Whenever you see issues, right? So you see issues, usually on the hardware, what is the first problem, the first thing you want to probe? Power, yes. So it has to be powered up at the correct voltage, and then what's the next? Ground. That's a one summer internship after that's the outcome. Even though it's very simple, but power and ground. So ground, how do you probe power? Easy, right? Multimeters, okay? Red probe to the power, and the black probe to the ground. right? You can look at the voltages. What about ground? How do you probe ground? How do you probe ground? 0 volts? No. How do you probe ground? Your the right probe to ground, to the ground of the chip, and then the black probe to the universal ground on the board. Then you probe, you'll see a 0 volts. Is that correct? Is that the legit way to do it? Nope. Because continuity check, right? You want to hear the beep. You change it to the contact. There's a option at the bottom labeled as contact, where it's a little bit different channel on the different multimeters, and you can do a continuity check. You hear the beep, which means they are shorted together. So the ground pin of the chip has to be grounded to the universal ground of the board. You have to hear the beep, okay? So that's how you verify power and ground. So if the power and ground are working, another thing. So when you are probing the power and ground, are you supposed to probe the pad or the pins? So you have the pin, right? Pin of the chip on the pad. So which one should you probe? Or you just don't look at it, just do it. Doesn't matter where the probe is probing. So here's the pin, here's the pad. Which one should you probe? Both. Okay? If you probe the pin, right, you see a voltage. No, if you probe the pad, you see a voltage. But if you probe the pin, there's no voltage. What's happening? The soldering issue, right? You want to reflow the solder. Just heat it up one more time to reflow it. And similar to the ground, if you probe it, you hear the beep from the pad, but then you move your probe a little bit away from the pad and to the pin on the top of the pin, and you don't hear the beep. It's a soldering issue as well. So you want to reflow the solder and fix that first. So if all the power and ground, everything works, what's next? The functionality, right? So for example, the IR emitter and the IR receiver, it's not working, and you see issues, and power works, everything works, but it's not working, right? So where do we want to start with? Fuse, no. It has power, right? What's the starting point? So you have to think about how it works, right? It has to emit first and then receive. So you want to probe the receiver, the emitter first. Okay, so how to check the emitter? So where's the emitter signal got started? The ping from the microcontroller, right? Because everything got programmed in the chip, and if that works, it should output PWM, right? So should output PWM. That's pin 45. Okay, that's pin 45. You probe pin 45, and from the oscilloscope, you see PWMs. All right, so the signal is out. And then you know it's out and 245, and it should go to, if you go to here, you probe 45, and you see it's out. However, still not working. And what you want to probe is, you want to probe the pins over here, because this is 45, and then you probe this point and see if the signal arrives here. You probe 45, it happens, but you probe this jumper here, it doesn't. What's the problem? I'm gonna, design some of the questions like this on the final exam, right? Okay, so I'll give you a lot of debugging problems over there. So if you probe 45, you got signal. If you probe the jumpers, there's no signal. What's happening? What's the problem? Let me show you the PCB here. This guy. Okay, where's 45? Here's 45. And I know 45, pin 45. On the right side? Okay. So pin 45 is directly, because this is the pin, if you look at schematic, right? So these are the header pins, right? So all these ones are directly shorted to the pin of the pin 45 of the microcontroller. So if you probe pin 45, which means there's a good connection, between that pin to the microchips, the microcontroller's pin. All right, it works. It delivers. It got delivered to the pin 45. However, if you probe this little jumper, you see this little jumper on the top. There's a bare metal on the top. That's designed for probing. Just let you guys know, okay? Because whenever you put a jumper on the two pins, the two pins are getting covered, right? But a lot of times people still want to probe it. How to probe it? That's why the little jumper has a bare metal on the top, so you can use the probe's hook to hook on the top. You can probe it. All right. So you put the probe on the top over here, and it's not showing the PWM. What's happening? It's the same signal line, right? Because the 45 is getting delivered. It's delivered to here. That's 45. Okay, 45 is here, but your probe here is not working. What's happening? Some of the soldering in the middle is not happening. Okay, so the traces or something getting damaged. If this one works, and you can probe this point, the other point, and you can find other thing, other places, and see, everything works. Okay. You could also probe this the emitter of the transistor and see if you can find pulses from the oscilloscope. If the pulses here happens, you know that kind of signal passes your LED. So the LED must already emitted something. Okay? It must emit something. If you see signal here, you know the signal passes or getting passed to this channel. So you know the pulses were delivered to the LED. However, it's still not working. What's the next? What's the next thing you want to do before you replace any components? Assuming the components are very expensive. So before you do anything else, and you know the pulses are delivered to here, is there any way that you can just detect it, or you can test it really quick? I would recommend that, because you'll know the electrical signals are delivered to the AR LED, but your board is not receiving anything, right? So you can find a different board, like whoever's board, or including my board, right? We know it works. We can only use the receiver, the decoder on that board, the functioning board, but using the emitter here. So this guy emits, but you know there's a functioning board, has a functioning receiver, right? And then you connect USB to the computer, and let this guy emits, and the functioning receiver receive it, and see if you can receive anything over there. Okay? And if you know the functioning board, the receiver over there works, and you know the electrical signal arrives here as well, however, you are still not receiving anything from the good board. What's happening? What's the possibility, or what's the next step should be? The code? I mean, it's task 1. It's given. Can I say it again? I will say it again. So, change what? No, before you change the component. So I know the electrical signal got delivered to this guy, right? And I know my board works. There's a good board over there. And I'm using this emitter to send signal to the other board's receiver, okay? But it's not receiving anything. Electrical signal arrives the LED, but it's not receiving anything. What's the next logical step? 2 steps. First, checking the soldering of the LED. Soldering. Reflow the solder at the pad of the LED. And I reflow it, I put a flux, I reflow it, still not working. What's next? LED is burned. Replace it. Okay? Then replace with the new LED, put on this old board. It should work. Okay, it should work after that. If it's still not working, maybe the BJT, you can replace the BJT, but it should work, okay? All right, so you can use a different board to check it. You can get a functioning one. It's like a positive control. You know, it's like positive control. You know it works. So you bring it into your design so you can reduce the number of variables on the board. So you can keep debugging in the same way, right? Reducing the variables and narrow it down to the problem to maybe just one single problem. So you can start working on that after that, okay? So debugging skills. Whenever you guys are doing your project, you got the PCB, you got your wiring on the breadboard, and when you're asking questions, never ask me that simple question anymore, okay? I won't help you if you just tell me the board is not working. I won't help you at all, Okay? I want to see some kind of analysis before you ask me that question. But don't be afraid of asking questions. If you really need help, I will still help you. But I mean, I just want to see like you go through that first. All right, so that's the first thing. I'm gonna do some snapshots and show you some connections of using these components. But before doing that, I'll show you some other project sensors I have in my lab, so you can consider using them as well. Again, so it doesn't have to be a very complicated project. You just need to use 2 different modules, and 2 ISRs cannot be in one loop. And there are so many different sensors that I have. I highly recommend you pick up one of them and put it in your projects, okay? So for example, the heart rate monitor is a module, and you are not designing the PCB yourself. You can directly connect these modules pins to your board, and it's an I2C protocol, which is really popular because it's not super high speed, but it's super simple. It's only 2 pins, 1 clock pin, 1 data pin. It's even less than the SPI, but you know, same number of pins as the UART, but way faster than UART. Right? It's a totally digital. It's really convenient and popular right now. So this is a heart rate monitor by detecting the pulses of the blood vessels in your fingertip. So here's a little sensor. It's also IR signal. It emit IR signal and then reflected by the blood stream in your fingertip, and then got reflection and received by the same chip, and it's detecting the blood being pumped to your fingertip. So that rate is calculated for the heart rate. So everything will be converted into a digital signal and being put in the I2C protocol. So directly sending out I2C signals. You can use the I2C packages. It's free. You just download it. It's everywhere for Arduinos. That's why we want to use Arduino. It's super simple. If I'm not asking you to do a project, but just use the Arduino board and interface with this guy, you can find an example online and just copy and paste the code. You can start seeing heartbeat or the pulses from your fingertip in probably 5 minutes. It's that simple, just to let you guys know. Very easy to use. You could definitely use that source code from any online resources and integrate that into your state machines, ISRs, for some kind of product design. It cannot be, you cannot just show me that this is working, right? This is from the online example. I connect to my board, this is a copied code, 5 minutes, works. I don't want to see that. It should be a one design. For example, you know, someone push a push button to start it, right? Like a product. You know, so have you seen this kind of product in the hospital? So the patients, they put a little clip on the fingertip, so that measures your heart rate, right? So similar thing, you press the push button, to start it, right? And then starts doing the calculations and eventually report it to can be a display module. And there are multiple display modules available. And you want to hear a little beep, so you can use a speaker to create that single beep. When you start it, it beeps, right? And then when something happens, or when the measurement is done, it beeps again. So that involves some ISRs and timers for the sound effect and measurements. So this could be another really interesting project you can do. And this webpage has all the instructions. If you are interested, let me know. It's already published. You can find it from. Let me see where I got it. So this is from the spring 2023's microcontroller class I taught, and this is the module we used. I still have a lot of these modules in the drawer, and these are the pulses that we detected. And you could use a little display module. It's the OLED display module. I have a lot of these in my lab to show the parameters, the vitals of that person. Okay? This is another project. And for this one, it could be really simple, because when you are trying to design the prototyping that design, you could just grab a breadboard, because all these pins are available. These are dip pins. You can directly plug into the breadboard and using jumping wires make the connections, right? And then try to program design your code. So when that is working, you just put everything on the PCB. It should work on the your PCB as well. So that's another these resources available for you guys. And also, not this one, sorry. What else we have? The LCD monitor. It's a really low cost monitor, just $1, $2 for each piece. But it's a very old design. If you don't want to use a smaller one, which use it's a I2C connection, you can also choose to use this one. That already shows you the connections, and the code is given. Again, so if you don't have to do anything else, just put the example on the breadboard, do the wiring, and download the code. It probably only takes you like 10 minutes to get it done. So you can show a lot of things on the monitor. And you can do a temperature sensor. I have all different kinds of temperature sensors. Could be a thermistor, detects, measure temperature by resistance. So temperature changes, resistance changes. So you can use a voltage divider to measure it. This is the ADC to measure the voltage changes and convert it to temperature. Okay, and also the temperature and the humidity sensor. So this one outputs both humidity and temperature data. So I have a lot of these sensors as well. If you want to measure humidity and temperature, you can choose to use this one as well. Shows you all the connections, and the code is given, right? So you can directly copy and paste. And we have remote controllers, all these receivers, decoders available, but different from the ones from our board. And okay, this is this one. And also I have, this is called a light, it's a LDR, it's a light dependent resistor. So depending on the intensity of the light, it changes the resistance, right? So you can measure the resistance output and convert it to the light intensity. So this is a light sensor. Okay, this can be used for the light control in the room, right? So all these kind of things. And I also have a little robots. You can also mess with the robots. I have all different kinds of code available, including the sensors. For the distance sensor, it's an ultrasonic sensor. One emits a sound signal, another receives the reflection. So you can measure the distance using a sound sensor. Its code is given, it's super simple to use. And these are the motor controllers, motor drivers. So what the robot can do is really simple. You can use a remote controller to control it. Okay, so it's a remote controller. So there's a receiver on the robot. You can use this one and receive the IR signal, right, and responds to it. So you can start it, and then whenever it's on the top of the black tape line, it starts tracking that path. So because it has the IR pyre at the bottom, so it detects the relatively lighter surface of the floor. So whenever it's moved onto the darker tape, it senses it and then just corrects itself. And also you can use, this is a distance sensor of the ultrasonic sensor. It measures distance. Whenever it sees the obstacle within a certain distance or range, it will stop and measure the surroundings and find a way out from the maze. It's not super intelligent because it's really simple loop, but it does the job. The success rate is probably not 100 because it's not AI based or something. It's really simple. You could also do that. The robot is available. You can modify it, design your own board to interface with that robot if you want. I have like probably over 10 or 20 of these robots in the lab. And if you want to move forward with some fancier design, doesn't mean it's complicated. It could do Wi-Fi. It's something invisible to people, so it seems like it's hard to control, but it's not, because all these wireless receivers are just nowadays are so reliable to use. You could do Wi-Fi, you could do 2.8 gigahertz, just a simple, very similar to the Bluetooth frequency. But it's all integrated into the module. You don't have to mess with RF. It's all integrated. It's all digital. Okay, so a project we did for Prusa Springs hot tubs is that we used this was the very first prototype we did, but now it's just a lot better, way better for the one we delivered to them. So this one has a Wi-Fi module. The Wi-Fi module receives a digital signal as a UART protocol from the pins. It's just receiving and sending signals through these pins digitally. And this is the antenna for Wi-Fi, so it's able to interface with the router in the room, and it measures the temperature data. So first it displays on the OLED monitor is 27.31 Celsius degree, and also it sends the temperature data to the internet through a cloud. It's called ThinkSpeak, right? So this was super popular a few years ago. I don't know if still very popular now, but you could send the signal through the router to this server, and you can use your phone, even use your phone and anything else, and to look at the temperature data on at any place on this planet. It's just as long as you can get into the internet, you go to that server, and you will be able to see the temperature data being measured. It's called IoT, right? Internet of Things. All right, so another project. And I also have different motors. This is the SD card module. This is the SP32. It's another very popular microcontroller that I can use the Arduino's IDE, the program, to code it. All right, so here's the chip. It's already included the microcontroller and also the RF stuff inside the chip. So you are not actually designing that PCB by yourself. What you need to do is just purchase this little module and solder it on your design. So we did it by the time, so the final product was sponsored by a company in Cortez. They're trying to put the very portable sensor can sense the speed or acceleration to the horse hoofs, and so it has to be tiny, right? So, and also has to be wireless, because there's no way that I can have a lot of cables connect to the hoof and then collect the data. So it has to be wireless. So there are multiple ways to do it, but eventually we found the Wi-Fi protocol will be the best. So we chose the ESP32, and we have to design a really portable and compact PCB. It's tiny, which can fit into the bottom of the hoof. And here's the PCB design, and that's the ESP32's chip, and that's accelerometer with a gyroscope. Okay, and that's a voltage regulator converts the one cell battery, because there's no room for multiple cells of LiPo batteries. Okay, so what's the voltage for one cell? No. Output voltage for one cell LiPo batteries. This is another important thing to know. Okay, that it can be in the interview. So it's standard, right? The LiPo batteries are standard voltages for the output. So one cell is 3.7 volts. So two cell, you can see some of the three cell batteries are 11.1 volts. So they'll tell you like the 3-cell LiPo battery has 3 cells in it, so it's stacked to each other onto each other, eventually giving you 3 times 3.7. So 3.7 volts, but all the components are requiring 3.3 volts as a power supply, right? In that case, when you are picking up the voltage regulator, usually they will lose some kind of voltage. All right, it's called a dropout voltage. So if you are converting a voltage to a smaller voltage, the regulator has to be very carefully chosen. So for example, the really cheap regulators, they are losing like 1.2 volts. If you are, 5 volts power supply from USB and you regulate it to 3.3 volts, is easy because there's like 1.7 volts room to drop. But from 3.7 volts to 3.3, you only have like 0.4 volts to drop. But most of the regulators cannot do it. So I have to use a certain regulator like this one, has a low dropout voltage, so it can convert 3.7 volts to 3.3 volts. It's a independent PCB with all the components on it, including the power supply pins. So you can also choose to use this one. And why I like this module a lot, because it's one of the most popular accelerometers on the market. If it's not a unique, only one available. I think if you really want to work on it, it's really simple. It's I2C protocol. I have tutorials over here. It shows you the connections, how to make connections to your. You can, if it's the Arduino, it will work as well. There are like millions of examples online, so you can measure accelerations and angles. So if you have acceleration and angles, you can calculate the position. If it's a flight airplane control, right? It measures the angles, so you can control the flights or the airplane's angles. I think these are called yaw, roll, and pitch, right? So these three different positions, and it's very useful. Think about humanoid robots. Okay, it's all about position design, angle measurement, and accelerations. So it's very useful. So knowing how to use accelerometers could be really useful actually. Because the humanoid robots probably will come to your house in 10 to 20 years and do all the chores for you. And Elon Musk was talking about, they can do a snapshot of your mind and copy it to the robot's mind, and so you can live forever. Could you tell the difference? If your memory, your mind, your thinking, and everything being transferred to a robot's brain, so that one will live permanently, and if you die, what's the difference? Like you die or you are still surviving? I mean, what's the difference? How could you tell? Since that thing knows everything about the past and has all the experience of the physical of yourself.
But if I die, I die.
How do you know if you died?
I'm not connected to the robot.
You are not, but the robot has all the memory and everything. Can you think about it? I don't know. It has all the experience, can do pretty much the same thing as what you can do, and remembers everything you can remember. And how could you know? Huh? What's that?
That's for the philosophers to figure out.
Yeah, probably.
Like it could be doing bad things after I die, and I'm not gonna know because I'm dead. But it's gonna pretend to be me and going around doing bad things.
How do you know you are dead? That's the thing, right? So the robots is another you. Right? Will replace you, and will be the same you, right? Anyway, so humanoid robots will gain a lot of momentum in the next few years. It's not in the movie anymore. It's just in reality, and accelerations will be a very important sensor in the robot, and also pay attention to hands, right? Because everything else is very simple, but hands is still a challenge. I think a lot of companies and investors are putting money in there to figure out what human hands can do, and try to put on the robots. So it could be a really interesting research area. Okay, so these are the sensors available in the lab. Feel free to propose it and discuss with me today, or send me an email. We can talk about it next week. So I care about your experience and whatever you can learn from this class, or if you are having fun, okay? Instead of, just giving you a hard time, even though that's also important. Challenge you is important, okay? Don't want to make it too simple. But more importantly, I hope you have some fun in this class. Have fun, okay? Which means a success, okay? Overcome challenges and also get a success.
This week wasn't fun.
I know, a lot of stress, right? But that turned you guys into a PCB designer in just a week. Okay? Now let's talk about the components on the PCB, all right? I'm gonna show you some of the connections. It's recorded, so always come back to this design. Also, another thing, so for the assignment due, is that due today? Okay. You only need to include 2 modules in your PCB. You don't have to duplicate everything. Only 2 modules. Okay? So we are not using that design as your final design because the final design is due probably next week. So it's not your final design. Just to let you guys start placing the microcontroller, to find the microcontroller in a certain place, so you know where to find it and place in the schematic, and make certain connections. All right? And then do some manual layouts over there. That's the goal. It doesn't have to be functioning, but I have to see that, hey, this guy is comfortable with PCB design. If I just give this guy a task to design a PCB product, he or she can probably get it done in a week. That's the goal, okay? So for the parts, there are several different projects you can think of if you are just trying to use the modules available on the PCB. So what are they? For example, I will give you the code, even though if you look at here, what? Okay. No internet again. That's why I just preloaded all the web pages before I came here. Still. Alright, so I will give you, so see the plan for this semester. You guys will be working on the ADC, right? So the data acquisition from the microphone, and that's doing an ADC conversion, and it also involves the microphone circuit, and it's able to measure the frequency of the signal, just like you guys know. So you will be able to measure the frequency of the audio signal from microphone, even though you haven't done that yet. But think about that. This is what you can do, okay? If you want to work on some kind of projects and using the code from this tutorial, okay, you can think about it. You can measure the frequency of it. So people are thinking about, okay, measure the frequency and create the light effects on the RGB LED. Fine, that's a good project. Okay, and after that, because I need to give you time to work on your PCB designs, that's why we don't have new lectures, new tutorials next week. So just come here and do the PCB and work on the project. However, the week after, we'll start the SD card. So you see that there's an SD card module on the back of the board. So for the SD, it's just so important. There are so many other important things I want you guys to know, but we don't have time to cover everything. So I dropped 2 tutorials. But you can see this is a tutorial I still want to keep in the semester. You just have to know it, okay? So SD card using a SPI communication protocol, and you need to talk about SPI and SD card during the interview for any of the positions in the industry. So SPI involves 4 different pins, and you need to know the name of the pins, and you need to know how to write data into the SD card and writing in blocks, or it's called pages, right? So this is all the things you need to, so the size of the page is 512 bytes per page, and you write page by page to the SD card and read page by page. So all these kind of things, and how do you log an audio signal and then play it back, right? So all these kind of things. So are you able to just directly use a microphone module to record something, or just record that audio and then play it back through the speaker easily? Are you able to do that? Think about it. How is that? How does that work? Think about that. The ADC is working really hard, right? So the ADC is digitizing the input signal. Okay, it's been digitized, and then you want to output that signal to a speaker and play it back. What's the challenge here? You have the speaker, you have the ADC, you have the microphone. Can you just use these 2 modules to make that happen? And how? Yes, pulses, but I mean you have to think about the intermediate process, right? Is that possible?
Well, you need power.
You need power, yes, but power is not a problem. What else? That's experience, right? So when you guys are in the industry, right? So you have to think about the feasibility of this kind of thing, right? So other people tells you, I just want to do this. You need to know these are the modules I need on the board. So the easy answer to this is no, okay? So think about it. If you digitize your audio signal and has to be stored somewhere first, and then you play it back by sending them out. Okay? So where do you store this data? If you don't have another SD card module, you won't be able to play it back. because the audio signal is being digitized, right? It's really fast at 25 microseconds per sample. It's a lot of data. And your chip, your microcontroller doesn't have the room to store this data. Okay? So in that case, you need an SD card. So it's basically doing this, right? Microphone, okay, digitization, speaker, and here's the reservoir, right? The SD card. It's doing sampling and sending signal to the SD card. Okay, at the same time, you read it out, and then play it. Or you can play it later. Okay? After you store everything, the whole song in the SD card, and after that, you can play it. Just send it out to the speaker and play it. So you have to use a SD card to do the job. And this will be covered in this tutorial, will be the last tutorial we have. And we will run out of time. No other time to do another one. Because we should, you guys should know I2C, the accelerometer, and you guys should know DDS, digital synthesizer as well, for digital to analog converters. But we are running out of time. Okay? I hope in this CE program we can have a microcontroller 1, 2, 3. Microcontroller 1, 2, 3 for 3 semesters turns you guys into an expert. Impossible. Unfortunately, impossible. Okay, now let's come back to the schematic. This is the last thing I want to talk about. 10 minutes left. Okay, let's talk about that. I'm recording this, so always come back to look at it. Okay, so for the necessary connections for different modules, starting from the power. Okay. All right, that's the starting point of your design. Not sensors, not speakers, not microcontrollers. Starting from the bottom left corner of the schematic, okay? After you place the frame in the schematic. Place this USB module over there. Okay, the power. And one more thing, I'll probably repeat it on Monday. So when you start a schematic, you keep drawing, keep placing parts in schematic. If you don't click that schematic to board button, you won't have a board window. Okay? You can work on the schematic, save it, close it, doesn't matter. Once you click that button, and there will be a layout window pops up, and you never want to close one of them when you are modifying one of them, the other one. Okay? For example, once you start it, you got a layout window, and then you are not thinking that you are going to modify it, so you close that layout window. And then you come back to the schematic, start modifying it further. What's going to happen? Yeah, they won't sync. There will be inconsistency issues the next time you open it. And that's super hard to fix. So you have to go back to the original step before you closed it, right? Whatever you have done won't work anymore. You have to go back to like whatever you did a week ago. It's a lot of pain. So keep both windows open once you have both files in there. For example, if you do see inconsistency issues, okay? Because your roommate turned it off for you for some reason. What could you do? Huh? Cry? Report that person? You just go back to your library, the project file, and you delete your board file, right? Delete it, so it doesn't exist in your design anymore, and then recreate another layout file to make it consistent. But all your manual layouts and everything, the placement will be gone. So everything will be at the bottom left corner, and you have to replace them in. But this is something you can do, right? But try to save copies and backups at a safe place. Always keep both windows on. So for the USB cable here, put this cable here. We're only using the power supply and ground, but nothing else. So for this one, okay, for this guy, these are not needed, right? This should be gone. And ground you need, power supply you need. This is needed. I just got pin 1. This is the fuse, right? Fuse is always helpful. It's always helpful. And this is a inductor. Inductor is rejecting what? AC noise. Is inductor a good component being placed between your component's ground and the overall global ground? Question mark. Is an inductor a good component to be placed between your chip's ground and the global ground? Question mark.
Yes.
Yes. Why?
Because ground is DC.
Yeah. Good. It's rejecting what? AC noise. But passing ground DC, so are getting a solid DC ground without any problems. So this is needed, right? So you got power, you got ground. What else? Now start placing what? Your microcontroller. Okay, your microcontroller. You need this area. So what do you need here? You need the oscillator. Yes. Power. This is power. Yes. VCC. Yes. All these things. You got another inductor here. Inductor doing what? Passing DC ground, rejecting AC noise. We'll be on the quiz, right? We'll be on the quiz. Do you need all these? Probably not. It's a product. I don't want to make it look like a prototype, right? You don't need these header pins. No. You just need to physically short the pins that are needed to your sensors and modules. Just physically connect them to your electricity. Unless you think this might go wrong, you leave a header pin there for probing, for debugging in the future. However, unless you need that, otherwise you don't. Do you need this? SD, SDL, you have to know it. Be on the quiz, even though we don't have I2C, but I will do whatever I can to make you more competitive for the interviews. Okay, so SD, SDL, what are these? These are I2C protocols. Okay, I2C. It's just a different digital protocol. It's SD and SCL, just two pins, DA, it's a serial data. CL is the serial clock. So so data pin is just one. Sometimes they call it one-liner. It's just one line for either sending and receiving. It's really powerful. And one clock pin to synchronize both the receiver and the transmitter for digital communication. Super powerful. You can see nowadays a lot of sensors are using I2C, including the display modules, accelerometers, and a lot of other things. However, we never use I2C for SD cards. If people in the interview, they ask you, what's a good interface or communication port for SD card? If they ask you, can you use UART or I2C for SD card? The answer is no, because SD card usually has like gigabytes of storage, and I2C and UART are so slow. There's no way that I can use I2C or UART. You have to use SPI, right? So SPI can run up to like 2 to 4 megahertz, and you are able to save and write and read a big chunk, a large amount of data from the SD card. Okay, so I have to use SPI. But I2C is slow and it takes less number of pin resources, and also it's able to do a long distance communication. But SPI is too fast. Long distance there will be a lot of parasitic capacitors, and will getting canceled to ground. Okay, so you need these parts, but you don't need I2C if you're not using it, and then just to pick up the pins you need and short them to your sensor to your modules. You need 2 modules. Okay, at least 2 modules. What else? What else do you need? If you are choosing, if you want to use like microphone and the speaker, for example, you are trying to record the audio signal and play it back, that'll be a lot of fun, right? You can talk to it. You can see the very typical applications. It's very interesting for the microwaves in the US. There's always a message button, right? But all the microwaves in China, they don't have this kind of feature. But in the US, you have a message, and you press the message, you can record something and It's probably for the parents who have to go to work in the early morning and leave a message to their children, or you have to leave a message to the roommates or something. But there's usually a message button, right? So it's basically you can design that kind of system by yourself after this class, right? So it's you put a little storage chip. Doesn't have to be SD card. Can be a different storage, just a memory chip. You can solder physically on the board. So that's a little double buffering, right? Why double buffering is also another important thing to learn, right? That's why we have to do SD card. Why double buffering? Because whenever this guy is filling up the buffer here by digitizing, and you are also writing the data to the SD card at the same time. So, but you cannot directly, write. You can not directly write data to the SD card using the buffer that is doing data acquisition at the same time. Has to be a different buffer. So whenever you have two buckets, right? So when this bucket is being filled up by water, and this and the other bucket was used for data acquisition before this, right? So now this is full, and you are dumping the water from the other bucket to the SD card whenever this bucket is doing recording, and then next time you swap it. Since you cannot, reading and write from the same buffer at the same time, so you have to use a double buffering. This is for like real-time data logging for a lot of large amount of data at the same time. Super important technology, right? So the microwave, the message button will do this job for you. So if you want to use that microphone, this module is required, right? And audio speaker, the audio amplifier is needed. And this is a low pass filter is needed for the readout. And you need an SD card module here as well, okay? SD card module. So the SD card is being powered up by 3.3 volts, so you also need a voltage regulator, which is this guy. Oh, no, not this guy. This is op-amp. You also need a 3.3 volts regulator. Oh, I already included over here. So that's 3.3 volts 3.3 volts output, right? It's taking in the 5 volts. Taking 5. Am I right? Something's off here. But that involves a lot of modules. I think, yeah. So this is 3.3 volts regulator. Yeah, this is the one you want to use. And if you want to use RGB, you know what the RGB module is, right? So the RGB module over here, and the IR here, and if you want to use the IR, right? The IR is the receiver. But keep in mind that sorry, I was wrong. So the SD card modules are here is for SPI communication. These two things are doing the SPI because the SD card is doing a 3.3 volts, and you have to convert it. This is a level shifter. It converts the 5 volts logic to 3.3 volts logic. So these two components are required for the SD card. And if you need a 3.3 volts power supply, that's the regulator you have to use. Okay, this is LP2985. You can see this regulator inputs a 5 volts voltage and outputs a 3.3 volts. It's just a voltage regulator. Output taking in 5 volts and output 3.3 volts. Actually, you can see we don't have too many components, too many modules on the Skyboard. And if you pick up two of the modules to make a really fancy project, that'll be really exciting. And I want to tell you that because we are not really doing that playback, audio playback experiment, because this one only has SD card reading and writing and SPI port. So if you would like to use if you want to really work on that playback project, I will give you the code for that. Okay, to reduce the workload of that one a little bit. If you want to do a microwave messaging system, you can name it that way. So you could do it that way, and I will give you the code. You only need to work on the hardware and modify the code a little bit. The code is based on the PIC microcontroller system, but the code is given. All the programming strategies showing there. Just have to translate it into a Arduino language. Super simple. Most of them are the same. Just some of the variables has to be declared. For the Arduino system. Any question on anything? We will work on the course project starting next week, from Monday to Friday, and so we can guarantee that by Friday you guys will have a good PCB, so we can send it out to JLC PCB for fabrication. Okay. You can add a logo to it, whatever logo you want to do. Okay. Could be your high photo. You take a photo. There's an online software, online tool that can convert your high photo to a print to the T-place layer on the board and print it on your PCB if you want. Any type of figures. Any questions? All right. That's it for today.